Welcome, everyone, to Research for Beginners. If you are new to statistics, research methods, or data analysis, this channel is designed exactly for you. Before we begin, I encourage you to subscribe to the channel, like this video, and follow us so you don't miss future tutorials on statistics, SPSS, Smart PLS, and research methods. In today's video, we will understand ANOVA, Analysis of Variance, using a very simple and intuitive example. Imagine you want to investigate whether the type of beverage a person drinks affects their reaction time. To test this scientifically, we divide participants into 3 groups. One group drinks water, one group drinks a sugary fruit juice, one group drinks coffee. After drinking, all participants complete the same reaction time test. Our goal is to find out whether there is any significant difference in reaction times across these 3 groups. Because we are comparing more than 2 groups, we use ANOVA. If there are only 2 groups, we use a t-test. We have a separate dedicated video on the t-test on this channel. Please check it out to understand when and how to use it.
Every statistical test begins with a null hypothesis, which represents the idea of no effect. In ANOVA, the null hypothesis says that the mean reaction time for all 3 groups is the same. In simple words, the null hypothesis assumes that drinking water, juice, or coffee makes no difference to reaction time. Our job as researchers is to check whether the data supports this claim or whether we should reject it.
ANOVA separates total variation into 2 key components. The first is variation within each group. This occurs because individuals in the same beverage group still differ in their natural reaction times. The second is variation between groups. This reflects the possibility that different drinks, water, juice, and coffee, may actually influence reaction time. ANOVA compares these 2 sources of variation to decide whether group differences are meaningful.
To simplify this idea, within-group variation represents individual differences and randomness.
Between-group variation represents the effect of the beverage. ANOVA asks a very simple but powerful question. Are the differences between group means larger than what we would expect from random variation alone?
Let's now look at example 1. The scores are sorted from smallest to largest so that patterns are easier to see. Within each beverage group, reaction times vary widely. Some participants respond very quickly, while others are much slower. When we compare the groups to each other, however, the groups look very similar overall. In this example, the variation within each group is much greater than the variation between the groups. This tells us that most of the variation is due to individual differences, not the beverage consumed. Therefore, we failed to reject the null hypothesis. Conclusion: the beverage does not have a meaningful effect on reaction time.
Now let's look at example 2, which shows a very different situation from example 1. First, focus on what is happening within each group. In the water group, the reaction times are 29, 29, 30, 31, 31. These values are very close to each other. This means people who drank water responded at almost the same speed. There is very little variation within this group. Now look at the juice group. 17, 18, 19, 19, 20. Again, the scores are tightly clustered. Individuals in this group behave very similarly. This also indicates low within-group variation. Finally, look at the coffee group. 10, 11, 12, 12, 13. Once again, the values are close together, showing very little variation within the group. Now, let's compare the groups to each other. The average reaction time for water is around 30, juice is around 18-20, coffee is around 10-13. These group averages are far apart from one another. This tells us that the between-group variation is much larger than the variation within each group. This is exactly the situation where ANOVA works best. People within each group are very similar.
Now let's move to example 3, which is a very important case to understand. At first glance, this example may look less obvious than the previous one. The differences are not screaming at us immediately, and this is exactly why we need ANOVA. First, focus on what is happening within each beverage group. For the water group, the values are 29, 30, 31, 31, 29. These numbers are quite close to each other.
This tells us that people who drink water reacted at similar speeds. For the juice group, the values are 28, 29, 27, 30, 29. Again, the values are clustered together. There is little variation within this group. For the coffee group, the values are 25, 28, 29, 27, 29. Once again, reaction times within the group are fairly similar. Key point: in all three groups, within-group variation is relatively small. Now let's compare the groups to each other. The reaction times for water are centered around 30. Juice are centered around 28, 29. Coffee are centered around 26, 29. The differences between these group averages are not extremely large, but they are systematic. This is why the slide says, in this case, the variance between and within groups isn't so obvious. When differences are not visually obvious, we cannot rely on intuition alone. ANOVA helps us by quantifying how much variation exists within groups, how much variation exists between groups. It then compares these two quantities mathematically. To understand whether groups truly differ, we first need to look at total variation in the data. Total variation simply means how much do the data values differ overall. ANOVA tells us that this total variation comes from two main sources. The first source is variation between the groups. This refers to differences in the group means. In our beverage example, this means, do people who drink water have a different average reaction time than those who drink juice or coffee? This type of variation reflects the effect of the treatment, in our case, the type of drink. The second source is variation within the groups. This refers to natural differences among individuals inside the same group. Even if everyone drinks the same beverage, people will still react at slightly different speeds. This variation reflects random variability, individual differences, and measurement noise. ANOVA works by comparing these two sources of variation. It asks a very simple but powerful question. Is the variation between groups larger than what we would expect just from random variation within groups? To answer that question, ANOVA calculates a statistic called the F ratio. The formula is F equals variance between groups divided by variance within groups. You don't need to calculate this by hand. Software like SPSS does that, but you must understand what it means. A large F ratio means the variation between groups is much larger than the natural variation within groups. This suggests that the groups do not have the same mean. In this case, we reject the null hypothesis and conclude that the treatment, in our example, the beverage, has a significant effect. A small F ratio means the differences between group means can easily be explained by within-group variation. In other words, the groups look different only because of randomness. Fail to reject the null hypothesis.
Now let's interpret the numerical results. The F value is 4.27. This represents how large the between-group variance is relative to the within-group variance. The p-value is 0.04, which is below the conventional threshold of 0.05. This means the result is statistically significant, and we reject the null hypothesis.
The results also report degrees of freedom, shown here as df equals 2, 12. Degrees of freedom depend on two things: the number of groups, the total number of observations. These values define the reference distribution used to test statistical significance. If you'd like a separate, simple video explaining degrees of freedom step by step, please comment below, and we'll create one to make it easy for you.
ANOVA can also be extended to more complex situations, such as studying how variance changes during the day versus night, or across multiple factors. Even in advanced designs, the logic remains the same. Compare variation between groups with variation within groups. If this explanation helped you understand ANOVA, please like, share, and subscribe to Research for Beginners. In upcoming videos, we'll cover SPSS output, post-hoc tests, and real research examples.